Hello everyone and welcome back to the C++ 3D game tutorial series. In this 26th video tutorial, we will face the first part about the making of a third-person game. In particular, we will see how to create a third-person camera specifically for a spaceship. We will rotate our spaceship through the usage of mouse movements, and in the end, we will translate it frontwards and backwards through the usage of W and S keys respectively. As always, we will face three main parts: requirements, design, and implementation of all the necessary things to create third-person movements. So let's start with the requirements. We need a C++ IDE, Visual Studio is recommended, the target platform is Windows, we also need DirectX 11 SDK, and last but not least, a bit of knowledge of C++ programming language is recommended. Now we can start the design part. Today we will finally see how to create a third-person game demo. In particular, in this first part, we will create a scene composed by the space, the player, that is a spaceship model placed on the bottom side of the screen, and for now, a single asteroid placed in front of it. We have already seen in the last tutorials how we can use materials, textures, and meshes to load and render one or more objects, more or less complex, on the screen, like the house, barrels, and wooden boards. And we have seen how we can merge multiple objects in one single merged mesh with the support for multiple materials. But now it's arrived the time to focus to the interactive part of our demo. The most important interactive feature that we have introduced so far is the first-person camera movements. Today, instead, we will see how to create further interactive features like the third-person camera movements for our spaceship, spaceship rotation through the usage of mouse movements, and spaceship translation frontwards and backwards through the usage of W and S keys. Good, so let's start with the third-person camera movements. As we have already seen in the 14th video tutorial, camera movements are made through the usage of mouse and keyboard input events. If we move the mouse along the x-axis of the screen, we rotate our camera around y-axis. If we move the mouse along the y-axis of the screen instead, we rotate our camera around x-axis. With the keyboard input events instead, we can translate our camera along specific directions. Good, but how can this be applied even for third-person camera movements? Let's see these images. In this moment, our first-person camera rotates in this way, centered in a specific position. Let's see now how a third-person camera behaves. This type of camera is usually placed at a certain distance from a specific position, usually the position of the player, and is rotated around that position. But how can we achieve this result concretely? Since we have already faced the making of a first-person camera, this effect can be easily achieved by rotating the camera as we have already done so far, by taking the forward axis or the z-axis. Let's remember that these axes are also called direction axis, that indicates the direction in which the camera is currently pointing to, and by moving along this forward axis of a certain distance in the opposite direction. This certain distance can be called camera distance. Let's remember that to move along a direction axis we have to use this linear algebra formula. where we need the initial position, the direction axis, and the distance. In this case, we have to negate the distance in order to go backwards. And this will be the final result. So far so good. The next step to do is to rotate our spaceship together with the camera. The rotation procedure will be the same used for the first and third camera. We will exploit the update model method to compute the position, rotation, and scale of our spaceship and in general all the various meshes we want to render. To do that, we will introduce two further vector 3D parameters, the rotation and scale parameters. Then we will compute the world matrix by multiplying the various transformation matrices in this order. At the beginning, we will compute the scale matrix and we will multiply it with the world matrix. And the same thing will be done for the rotation x matrix, the rotation y matrix, and the rotation z matrix. At the end, we will multiply even the translation matrix. At this point, we will have a complete transform matrix that considers position, rotation, and scale. This will be the result. But the spaceship placed exactly to the center of the screen doesn't allow us to see the scene in front of us. For this fact, we should place the spaceship a bit down towards the bottom of the screen. To do that, we can apply the same procedures just used. Simply, after we have moved our third-person camera backwards of a certain distance, we further move our camera along the y-axis of another certain fixed distance, like 5 units. Very well, now we are able to see both the scene in front of us and the spaceship. The next and last part to face is the translation of the spaceship. In particular, we want to move the model frontwards and backwards by following the forward direction and so the z-axis. We have already seen this particular movement with the first-person camera. The approach is the same. We need the initial position of our spaceship, the z-axis from the current rotation matrix, and the amount of distance. At this point, we have to use, again, the same linear algebra formula. At the end, this will be the result. Very well, now we can start the implementation. As first thing, let's add a new class and let's call it Space Shooter Game. Let's start to copy and paste the contents of app window class files to the Space Shooter Game class files. At this point, let's substitute the app window name with Space Shooter Game name through the Find and Replace function by pressing the Ctrl and F keys. Let's do the same thing in the main C++ file. To be sure that everything has been done right, let's build it. Good, it works! At this point, let's add a new filter in the App filter, and let's call it Old Demo. Here we can move all the files of the previous demo. At this point, we can add a new filter. Let's call it Space Shooter Game. Let's move the Space Shooter Game class files just created. Very well. To start, let's improve the mouse placement at the center of the window. So let's go to Windows C++ file and in the Get Client window rect, let's add the client to screen Win32 API function. This function allows to retrieve the current position of our client window in screen coordinates. With the window position in screen coordinates, we are able to place correctly the mouse cursor exactly at the center of our window. Let's go to Space Shooter Game C++ file and let's modify a bit the code in onMouseMove method in order to place our mouse cursor to the center of our window. Let's see if it works. And it works! Despite the position of our window, the mouse cursor is always placed at its center. The next step to do is to change a bit the way in which we switch from play to pause mode, and the other way around. At the moment, we are using the G key. Let's use the escape key instead. But only to switch from play to pause mode. To switch from pause to play mode instead, let's use the on left mouse down event. there is a little problem here. It is probably related to the swap chain resize. So let's go to onSize method. Here we are not considering the left and top values, so let's fix it. Very well. The further step to do is to go to update camera method. Here we are computing the light transformation. Let's move this piece of code in its suitable method update light. Let's move the light rotation matrix as an attribute of Space Shooter game class. And in the end, we can rotate the light just off 45 degrees around the y-axis. Let's go ahead and let's go to the render method. Here we are calling update, the method in which the transfer matrices are calculated. Render is not the most suitable method in which to call update method. Let's move it inside onUpdate event instead. Very good. At this point we can start to think about the creation of our scene. Let's start to add a directional light. So let's create the directional light vertex and pixel shader HLSL files. We have just created this shader previously and it's available inside the Earth shaders. Let's copy and paste them. Some parts of the vertex and pixel shaders need to be updated. For example, the constant buffer structure has been changed. Let's copy and paste it from point light shader. Vertex shader seems to be okay for now. Let's go to pixel shader. Here we can remove all the useless texture sampler used for the rendering of the Earth. For now, we need only the color map. Let's modify the texture coordinates as we have already done in the point light shader. At this point, let's change the code in the same way we have already done in the 19th video tutorial for the directional light. Once we have finished, let's go to Space Shooter Game C++ file and in the onCreate method, let's change point light shaders with the directional light ones, when the material called matte is created. In order to create the material for Skybox, we are using the vertex shader of point light and pixel shader of the Skybox. Let's create a vertex shader exclusively for Skybox in order to better organize the various shaders. As the first thing, let's add a new filter and let's call it Global Shaders. Here, let's move all the light shaders we have created so far. So, the point light one and the directional light one. In the end, let's do the same thing for the skybox. These are pretty common shaders that can be easily shared across various demos. Well, let's create the skybox vertex shader. Simply let's copy and paste the point light vertex shader into it. Let's change their name even in onCreate method. And let's see if it works. And it works. Now, it's arrived the time to clean some old and useless parts of code. In Space Shooter game header file, let's remove all the attributes related to old stuff and previous demos, like house, barrels, wood materials, house meshes, and so on. Let's leave only the resources related to Skybox and the material called matte that we can rename with a more suitable name like base matte. Now, in the Space Shooter game C++ file, we have to fix all the errors related to the removal of all the old and useless attributes. Good! Now we are ready to concretely start the creation of our Space Shooter game. Let's start by using the stars map as skybox. Let's see if everything has been done, right? Yeah, it seems so. The immediate next thing to do is obviously to add the spaceship player. So in the space shooter game header file, let's add the texture, material and mesh resource attributes. In the onCreate method, let's load the various spaceship resources. Let's clean a bit the code here by moving together related pieces of code. Now we can go to render method and here let's start to render our spaceship at the origin position. Let's see if it works. And it works! But the spaceship is not enlightened so much. So let's change the light direction. Let's go to Update Light and here let's rotate our light around X and Y axis of minus 45 degrees and 45 degrees respectively. Good! Now our spaceship is enlightened so much better. In order to have a landmark in the scene, let's add an asteroid object. So let's do the same things we have done for the spaceship. The only thing to change is to move our asteroid of 20 units along the z-axis. Let's see if it works. And it works. At this point, let's create the third-person camera. So let's add the update third-person camera method. Let's copy and paste the code of update camera method. At this point, we have to add a new vector 3D attribute that we can call camera rotation. Let's use its x and y values to calculate the camera rotation matrix. There is a problem though. So far we have calculated the rotation along x and y axis in the onMouseMove event. Instead, this calculation should be moved in the update third-person camera method. But we need some data, that is, the difference between the new and old mouse cursor positions, that is exclusively calculated inside MouseMove event. Let's store this data in suitable float attributes that we can call delta mouse x and y. So let's calculate the final rotation inside update third person camera. let's fix even the update camera method. At this point, we have to deal with the placement of the camera. We need two vector 3D attributes, the camera position and even spaceship position. For now, the initial camera position will be equal to the spaceship position. As we have already seen in the introduction, now we need the camera distance. So let's add it as a new attribute. And let's set a distance of 14 units. Now let's fix some cast problems in on-mouse move event. And as very last thing, let's go to update method and let's substitute the update camera with update third person camera. Let's see if our camera works, and it works. But if we rotate over 19 degrees around the x-axis, the scene is shown upside down. So let's go to update third person camera, and here let's fix this issue by preventing to rotate over 90 degrees or minus 90 degrees around x-axis. It seems to work. At this point, it's the turn of spaceship rotation. So let's add a new method and let's call it update spaceship. Let's copy paste the code of the third-person camera. Now we have to add a new vector 3D attributes for spaceship rotation. At this point, let's replace the camera rotation. We have to remove also all the part related to the computation of view and projection matrices, that here is useless. Let's go to update method and here let's call the update spaceship method. At this point we have to go to render method and we have to place and rotate our spaceship through the usage of the vector 3D attributes added previously. But update model method doesn't allow for now to rotate models. So let's start to introduce two new vector 3D parameters in the update method, the rotation and scale parameters. Let's compute the world matrix as we have already seen in the introduction, by starting with the scale matrix, then with rotation matrix, and as last thing with the translation matrix. Now we have to fix all the issues related to the update of the method. Let's see if it works. And it works. But the light seems to follow the rotation of the spaceship. Let's see why. Let's go to directional light vertex shader. Here is why. Because we haven't transformed the normal vector from model space to world space. Let's fix it by multiplying the normal with the world matrix. At the end, let's remember that the normal is a unit vector. After the transformation with the world matrix, the normal vector is not more a unit vector. To retransform it to a unit vector, let's use the normalize function. Let's see if it works. And it works. But the spaceship is placed to the center of the screen. Let's place it a bit down. Let's go to update third person camera and let's add to the current position the translation along the y-axis of 5 units. Get Y direction has not been implemented in the Matrix 4x4 class yet. So let's implement it. Let's remember that the y-axis is stored in the second row of the rotation matrix. Good, let's see if it works. And it works. As very last thing, let's go to update spaceship method and let's implement the spaceship translation in the way we have already seen in the introduction. Finally, let's go to update method, and since the update third person camera depends on spaceship position, we have to call the update third person camera method after the update spaceship method. Let's see if it works. And it works! That's all for now, folks. Today we have seen how to set up and create the first part of our third-person game. I hope you enjoyed this video. See you soon. Thanks for watching.